we were thinking about the theory of well orders, and we're leading up to the definition of ordinal numbers, which are going to extend the natural numbers. But at the moment, we were just proving some sort of library of basic facts about order isomorphisms between well orderings and themselves, or well orderings and their possible and initial segments. And we're building up to the idea that an ordinal is going to be a set that's going to be well ordered, and it'll be transitive. Now, it'll be well ordered by the epsilon relation. If you think about how we defined via von Neumann's definition the natural numbers, you'll see that they again satisfy this. Of course, a natural number, being the set of its predecessors, is just a finite set. So the ordering we had on the natural numbers, the less than, was just set membership. And that's going to be a well order because it's a finite total order. But we're going to have infinite sets being ordinal numbers to get some infinite arithmetic going. And these will also be well ordered by the epsilon relation. So we are up to lemma 3.8 at the end of the last lecture. So I'm going to continue straight on from there with lemma 3.9. So this is page 26, very bottom of page 26 here. So let's see what 3.9 says. Oh, as usual, send through any questions that you might have in the chat. So any well-ordered set, X with a less than here, is order isomorphic to the set of its initial segments. Where the ordering on the initial segments is proper inclusion. Right. So this rules out being equal. So it's a subset and not equal here. So recall an initial segment is, we pick some u in X, and it's of the form XU with the less than, and XU is everything that's earlier than U. So this is the W's that are in X, where W comes before U. And there's an obvious picture here. Here's X, here's some U, and then here is X sub U, right? Consisting of these W's down here. So the lemma says the picture of X that we have here actually is the same picture if I just think about subsets of X, where the subsets are all initial segments. So to say that U is less than V is going to be just tantamount to saying XU is a proper subset of XV, which is kind of obvious from the picture. And indeed, it's a two-line argument. So we just let y be the collection of these initial segments. Then the map that goes from A to XA, this is 1 to 1. So this is a 1-to-1 mapping from X onto Y. Okay, so 9 o'clock on a Monday morning. Why is it 1-to-1? You pick A and B and X. One of them is less than the other. Then A is in XB, but it is not in XA. So XB and XA are different. Okay, the initial segment does not include the element that determines it. It's everything up to that comes before that element. So this is a 1-to-1 mapping. And I've just kind of given the argument there. Since A is less than B implies that XA is a proper subset of XB, it's order preserving. So I've got an order preserving bijection between X and the set of its initial segments, ordered by strict less than. So the mapping is an isomorphism. So X with less than, it is indeed order isomorphic to Y with proper subset. Okay. Okay, let's then move on to ordinal numbers, unless there are any questions. I may do some of these exercises in the problems class tomorrow, 3.5 and 3.6. I'll see. Okay, so we generated this sequence using the successor. So this was generated using the successor function. Right? S of U is U together with singleton U. And according to the von Neumann definition, we use the names for them. And as you can see, each is the set of its predecessors. And indeed, we set for natural numbers, n is less than m if and only if n was a member of n. So we could define less than by set membership. And we want the same thing to happen for our transfinite ordinal numbers. So we should want the same properties for our ordinal numbers in general. So if we would define what an ordinal is by another property that the natural numbers have, so these were also all transitive. Okay. 2 is a member of 3, and also 2 is a subset of 3. Members were subsets. So the key definition for today is what an ordinal is. We'll say X with epsilon is an ordinal if 2 things hold. It's a transitive set, and epsilon has to be a strict total well ordering. So if I write less than for epsilon, then this is a well order. So I just call it a well order. So it's going to be a strict total ordering. Any subset of X must have a least element. And this is exactly what we had for the natural numbers. So our prime example we've already seen of a non-finite ordinal is omega itself. Example. Omega of epsilon is an ordinal. It was transitive, and epsilon well orders, or less than well orders omega. Sorry, 321. This is 311. 312. So we'll now look at some just general facts about abstract ordinals. And later on, we'll look at some more concrete orderings that will provide us with further examples. I mean, what we're going to have, let's see before we do this, what we're going to have, if X is an ordinal, then successor of X is an ordinal. Right, this is to come. Right? So we're going to have that omega union singleton omega. This will be an ordinal. We'll call this S of omega, or in other terms, we eventually call it omega plus 1. And then the successor of omega plus 1, right? This will also be an ordinal as well. So this will be omega plus 1 together with omega plus 1. And we're naturally going to call this omega plus 2, and so on. So this is all to come. But first we'll just do some slightly rather abstract results which just follow from our definition before we start thinking about these. And 312 is the first of these. So if I have an ordinal, then every element Z of X here is identical to X sub Z. So it means it just equals, right? This is the initial segment determined by Z. So this is a very special property of this ordering. Right? Because of the way we define it, Z is just equal to the set of its predecessors, which is this. So Z equals the initial segment determined by Z. This, of course, does not happen in general for well orders. So just to spell it out, Z equals XZ. And this is the set of things in X which come before Z. Okay, so this is special to ordinals. I just want to emphasize again, right? A general well ordering, you don't have that an element is equal to the set of its predecessors. Again, this is just a consequence of the definition here. Okay, so we suppose X is transitive and epsilon well orders X. That's what it means to suppose that X is an ordinal. Pick a Z in X. Then to be in this initial segment, this is true if and only if W is in X and W is a member of Z. But this holds because X is transitive. This one here holds because X is transitive. Because if any element of an element of X is already in X, so I don't need this part here. Again, because if Z is a member of X, it's a subset of X. So I don't need this condition. So I appeal to the fact that X is transitive for the implication in this direction here. But that's just saying these two sets are the same. And that's all you need to say. Great. So what we're doing then is generalizing what we had for the natural numbers. We had that if you looked at 3, okay, this is the set 0, 1, 2. 2 is a member of 3. If you looked at the initial segment of 3 determined by 2, this is just the collection of things in 3 where U comes before 2. Yeah, and that is just 0, 1. Right. But this is just the things that come before 2. It's just 2. So the initial segment of 3 determined by 2 is 2, just as what the lemma is stating. So our definition of ordinal gives us this property. Okay, so we're going to see that there are many ordinals that are not natural numbers. There are many infinite ordinals here. So one thing to note then, we've already defined what less than will be on ordinals. It'll be the same as epsilon. Right? So if this is an ordinal, as A equals XA, for any A in X, that's just the last lemma. I pick any other B in X, right? And what we're going to have is that A comes before B here, will mean that A is a proper subset of B. A is a member of B, but B is not a member of A. So A will be a member of B, and all the predecessors of A are also going to be in B. So I could write this like this. And we saw in 3.9 that a well-ordered set is isomorphic to the set of its initial segments under strict inclusion. So that's what we're saying here. But because A equals XA, we've got also this equivalence as well. So being a member is the same as being a proper subset. Again, this is just true for ordinals. We don't expect this for general orderings. So 3.14. If Y is a proper subset of X, where X is an ordinal, and often I'll just drop the pairing here and writing down epsilon. I'll probably just say things like X is an ordinal, because the fact that the ordering on X is always epsilon, that's understood. So I'll abbreviate this by just saying with X an ordinal. So X is an ordinal, Y is a proper subset. If Y is also an ordinal, then it must be an initial segment. Then Y is an initial segment under epsilon of X. So as a picture, here's the ordinal X. Y is a subset of X. Here. But the lemma says if Y is an ordinal, it can't be just, its elements can't be scattered through X. The element Y has to be an initial segment if it's going to be an ordinal. So let's see the proof here. So let Y and X be as supposed. So I'll pick as something in Y. So pick some A here in Y. Then as Y is an ordinal, we've just shown that A is the set of its predecessors. But if A is in Y, Y is a subset of X. So A is in X. So A equals XA also. Right? Again, so here and here, this is just the previous lemma. So XA equals YA. Now, Y is supposed to be a proper subset of X here. So Y is not all of X. So let's look at the least thing in X that's not in Y. So let's look at the Z's in X such that Z is not in Y. So as Y is not all of X, this thing here is not empty. So we've got a non-empty subset of a well order. So there is a well order less than least element of this set here. Well, here the ordering is epsilon. So it's saying there's an epsilon least element of X here. So let's call it C, infimum, the least element here. C exists as X epsilon is a well order. And the set is non-empty. So what we have then here is this must be C up here. If I pick something that's in Y, the set of things that are in Y that are less than A are actually everything that's in X that's less than A. So there are no holes down here in Y. This is XA, and this is the same as YA. So picking anything in Y, all of its predecessors, thinking of it as an element of X, are also in Y. So this bar, this is Y is solid all the way up to the least point, which is not in Y. And there is a least point not in Y because Y is assumed not to be all of X here. So what we have then is that Y is everything that comes before X. Sorry, it comes before C. So that is 314. So we're going to build up further facts about ordinals, probably for the rest of today and tomorrow. $3.15. If I've got two ordinals, their intersection is an ordinal. Right, so transitive sets well ordered by epsilon. Their intersection must be a transitive set well ordered by epsilon. So I just have to prove two things. So if X and Y are transitive, this is just a property of transitive sets. So the first condition for this to be an ordinal is satisfied. But if epsilon well orders X, it well orders any subset of X.
There's a question in the chat.
Right, I'll just finish this phrase. So as X is well ordered by epsilon, so is any subset of X. So in particular, X intersect Y is well ordered by epsilon. So that's the second condition for this to be an ordinal. It's transitive and well ordered by epsilon. Are we not doing lemma 313? Let's see what's happened to 313. Thank you. Yes, let's go back to it. Any epsilon initial segment of an ordinal is an ordinal. So I take an ordinal X, and epsilon is itself an ordinal. And again, it's an example of just verifying the two facts to be an ordinal. It's transitive, well ordered by epsilon. So let XA be an initial segment of X for some A and X over here as epsilon well orders X. So it's a strict total ordering. Any non-empty subset of X has an epsilon minimum element. It well orders any subset of X. So in particular, it well orders XA. So this is a well order. Now, the other condition is that it should be transitive as well as being a well order. So so I'm just seeing what notation that I've got here. I seem to have gone from U to A here. I've got that A equals XA. This is by lemma 312. Okay. So I pick something that's in A. I want to have that T is in A. And that will make A transitive. Any element is a subset. So I pick an element T of this element of A here. But A is itself just the set of its predecessors here. So what I have here is that then that T is a member of XA. So T is a member of A. So A is transitive. As well, A equals XA. So I've got that it's a well order and it's transitive. So it's an ordinal. Okay. Sorry, jumping about. Let's then jump back to 316. So actually at this point, we could do the exercise. We've proved enough lemmas here to show this. If X is an ordinal, so is Sx here. Now we've got a classification theorem for ordinals. Given two ordinals, we can compare them, right? In fact, one is either they're equal or one is a member of the other. Being a member of the other would mean it's an initial segment. So I take two ordinals, X and Y. So there's only three possibilities. Either X equals Y, or one is an initial segment of the other. So we've seen that being an initial segment of an ordinal is the same as being a member of the ordinal here. So by 314 and 312, this is equivalent to saying one is an element of the other. So there's only three ways about it. I'll think of them either being equal or one will be shorter than the other, because one is a member of the other or one is an initial segment of the other. Okay, so we'll see why this is the case. So proof here. Okay, so we'll suppose that they're different. Suppose they're not equal to each other, and we show the other alternative holds. Suppose they're different. Now, the last lemma showed their intersection was an ordinal. So what the outcome is depends upon what this intersection is. So there's an either or here. So either X is a proper X is a subset of Y, well, and a proper subset because they're different here. Or two, Y is a proper subset of X here. Since X is different from Y, in case one, this is saying then that this must then be an initial segment of Y. Sorry, this says case one. Case one here. X intersect Y is an initial segment of Y. This was because 313, if you look back to 313 says, right? Sorry, do I mean 313? What I've got is 315 is saying it's an ordinal and it's a proper subset. So by the last lemma, it's an ordinal. X intersect Y is an ordinal. And then $314, I think I'm appealing to here. There's a slight misprint here in the notes. By lemma 314. I think the notes say lemma 313, but the numbering seems to have gone astray. Or case two, it's the other way around. It's an initial segment of X. Okay, so here we had that X then ends up as an initial segment of Y, and here we end up with Y is an initial segment of X. So for this, in this scenario here, the lemma is proven. And we assumed X was different from Y, and we end up with X being an initial segment of Y or vice versa here. But there is an or case that we have to rule out. We've just said here, X intersect Y is either X or it's Y. And then the or case is that it's neither. It's a proper initial segment, both of X and Y. And we rule that out. We show that doesn't happen. So or X intersect Y is an ordinal that's properly contained in them both. In both X and Y. And we show this can't happen. So the analysis under either above was sufficient. and proved our result. So the analysis under the either suffices for the lemma. So again, by 314. X intersect Y, which we do know is an ordinal by the last lemma. It's an initial segment of both X and Y. So simultaneously, an initial segment both of X and of Y. So let's say X intersect Y is an initial segment of X, and it also is the initial segment of Y for some A in X and B in Y. So I'm not sure how good a picture we can draw. Here's X and here's Y. And here is X intersect Y. It's a proper subset of them both. In fact, it's an initial segment of them both. And here's A and here's B. And X intersect Y is XA and it's YB. But now we appeal to the lemma that says that for ordinals, and just for ordinals, an initial segment just is the element that determines it. So by lemma 312, A equals XA, and this equals YB here, but this equals B. But neither of A or B are in this intersection. Recall the things in the initial segment are the things strictly below A, and here are the things strictly below B. But now here we've got something that's not in X intersect Y, but it's in both X and in Y. So it should be in the intersection. And that's a contradiction. Hence, A equals B is a member of X intersect Y here. But X intersect Y is, for example, XA. And now I've got A is a member of the initial segment it determines, which is nonsense. So that's a contradiction there. So that finishes the lemma here. Right? Because I can't have A's in XA. So this picture doesn't happen, right? So if X is different from Y, it has to be all of X is somehow shorter, looks like an initial segment of Y, or the other way around. X looks longer than Y. Y is an initial segment of X. Yeah. Okay, fine. that's all for now. So for tomorrow, we will continue on with this and again, give some more concrete examples of ordinals, I think, towards the end of the next lecture.